Yeah, thank you for inviting me, and it's a pleasure to talk about my recent work on complete Riemannian four manifolds with uniformly positive scalar curvature metric, and this is a joint work with Otis Chodosh and Davi Maximo. So to just for the motivation part, um, one of the promising open problem in four manifold topology is to understand smooth structures on four manifold. Now, the famous open problem or conjecture in this field is Poincare conjecture, which asking if S4 has unique smooth structure. Oh, sorry. Um, so the motivation of this project is somehow motivated by this problem or answering this problem. So in the world of topology, people have been trying for long enough to find mostly a counterexample of this question, in a sense that many people believe that smooth 4D Poincare conjecture is false and S4 could have more than one smooth structure. However, we didn't able to find any counterexample so far. So maybe it's a good time to start thinking about this conjecture, or what are the ways even we can potentially prove this conjecture. And this is when I met Davi and Otis, and we started talking about various geometric arguments that could help us to understand a part of this conjecture, or if with some presence of geometry can help us to solve this problem or not. Okay. So, okay, but to start with, let me give you an example why four manifold in general seems very wide. So this is a theorem which is contributed to many people, such as Moncrief, Stalling, Friedman, Donaldson, Taubes, Gong, and many others probably. And it says as follows that Rn has unique smooth structure if and only if n is not equal to 4. And R4 has uncountably many different smooth structure. So somehow the 4 dimension is the one of the wildest dimension where things could get absolutely crazy. And when I was a grad student, this result in my first year of grad school really fascinates me. And probably one of the reasons then I started thinking about 4 dimension, seeing this wild nature. Um, so
Anubhav, may I ask a question? It's basic and maybe too simple,
Mhm.
but let me ask it. So these different smooth structures, are they diffeomorphic or not?
Yeah, so okay, great question. So when I'm saying different smooth structure, that means um, R1 is homeomorphic to R2, which is homeomorphic, let's say R4, but there do not exist any diffeomorphism.
Okay, so these are non-diffeomorphic
Yeah.
smooth structures. Okay, thank
So
you.
yeah. So that the meaning of different means non-diffeomorphic.
Yeah, okay, thank you.
Yeah. So also sometimes in literature we call them exotic smooth structure. Exotic smooth structure. Yeah, sorry. Yeah, please ask me any questions if you have any confusion, because I'm like very used to of giving talks in front of four manifold topology. So sometimes I just like use various terms that may not be familiar to various people. Um, or also I could say something absolutely wrong. Um, okay, um, so so from here we got the motivation to study then that what if so the basic question is now that if existence of um, uniformly positive scalar curvature on four manifolds can help us to understand the smooth structure. So it sounds a very vague at this point, but I'll try to make it more precise with time. Um, so just to give you some evidence, what I meant, so there is a theorem by Chang, Weinberger, and Yu, who shows that R3 is the only contractible three manifold that admits a complete uh, Riemannian metric with uniformly positive scalar curvature. And this result kind of give us the motivation to ask the same question in dimension 4, or to study the same question in dimension 4, that whether R4 also be the only such manifold or not. In other words, whether although we saw that there could be uncountably many smooth structure which are non-diffeomorphic, but if we now also add this extra hypothesis that these manifolds have uniform positive scalar curvature metric, then is it the unique one or not? Okay, so to state our result, first let me define a standard notation. Um, so we call a contractible or manifold Mazur if it admits, sorry, a Morse function with exactly one critical point of index 0, 1, and 2. Or in other words, it will have a handle decomposition of, sorry, with exactly one 0 handle, 1 1 handle, and 1 2 handle. So such notation in general in four manifold world we call as Mazur manifold. Um, so here is the theorem. It is joint work with Otis Chodosh, Davi Maximo, and myself. And it's as follows that let M be interior of, by the way, if you cannot read my handwriting, please let me know. So let M be interior of a compact smooth contractible Floer manifold. If M admits a complete uniform PS symmetric, then W is homeomorphic to Floer ball. By the way, as I said, that this is homeomorphic, so it may not be diffeomorphic. But moreover, if W is Mazur, that is, if it has a Morse function with one critical point of index 0, 1, and 2, then we can prove that W is diffeomorphic to Floer ball. So that means we can improve the homeomorphism type to diffeomorphism type. So any questions regarding the statement of the okay.
That's very clear.
Okay. But notice that, so this above results discarding every possible other possibility of Mazur manifold or any other contractible manifold to have a complete PS symmetric, uniform PS symmetric besides R4 or its exotic structures, right? So the next result, same. So
So
let's
is it known whether there are Mazur manifolds that are not diffeomorphic to the Floer ball without the
yes,
assumption?
yes.
Okay.
Because Mars. So also let me point it out that this same problem has been studied before by Chang, Weinberger, and Yu, and they shows that some class of Mazur manifold do not admit interior, do not admit such metric, but we actually gave a complete answer that saying that except for ball, no Mazur manifold can admit such metric. But yeah, there are like using some kind of handle calculus in dimension 4, you can construct many example of non-trivial Mazur manifold because you can construct such a way that the boundary has non-trivial pi 1. So that way, then it cannot be diffeomorphic to standard 4 ball. But this particular result saying that those manifold then cannot also admit PS trick. Okay, but then the only remaining case now could be potential exotic R4s. And as I said, that there are uncountably many exotic R4s. But however, at least we able to like say that some of them do not actually admit such metrics. So this is second result by same authors.
Sorry, Anubhav, can I ask a question?
Sure.
So does the Mazur condition imply that there's critical points of index only 0, 1, and 2, or could you also have 3 and 4?
Yeah, so only exactly one index 0, one index 1, one index 2. Yes.
Okay, so I should think that these critical points cancel out in your, they
Yeah.
cancel out.
Yeah. So yeah, PSC metric, essentially this is the part. You are right that PSC metric forcing this critical point of index 1 and index 2 to cancel out then.
Okay, thanks.
Yeah. Okay. Any other question? Okay, so and so the second result, what we are able to show is that there exist uncountably many exotic R4s that do not admit a complete metric with uniform PSC. So although we do not know whether all exotic R4 can or cannot have such metric, but at least we have a good list of exotic R4s at this point. In particular, we can make it an uncountable list where they do not admit such metric. And so that this is a good place to actually propose this question then. So question is that is standard R4 the unique smooth contractible for manifold that admits such metric. And again, this question was previously proposed by Chang, Weinberger, and you. And now we are giving good evidence that this should be the case. And as I said, this is the reason at least I'm very interested in this question, because I feel that maybe uniform PSC metric can actually gives you some more information about smooth structure. So any comment or questions regarding the statement? So rest of the time, I'll try to give some sketch of how to prove such results.
It also makes sense to ask the same question about positive but not uniformly positive.
Yes. So yeah, I plan to have a few questions for the very end. So
Okay,
that's
yeah.
the question. Yeah. But okay, since you already mentioned that, see, in all our results, we need this assumption of uniformity. What happens if we drop this and just ask if PSC is enough or not? We don't have any answer at this point, but maybe or maybe give some answer. Okay, thank you.
Perhaps you could put the definition of uniformly positive scalar curvature.
Oh,
I think most of us know it, but just for the audience in general.
Yeah, so uniformly positive, we just assume that the curvature pointwise. So the curvature is greater than equal to 1 at each point. Okay, so now I'll tell you some of the tools that could be helpful to understand or answer such questions. So, so there are sort of two tools or two type of tools that we'll be using here. One tool coming from the world of geometry, and one tool coming from the world of topology. So, sorry. So let me talk about the geometric tool. And I think to some of you, this is famously known as the mu bubbling. So I'm not going into the details of these tools, but I'll just state the result that I'll be using throughout the rest. And this is a theorem or proposition by Gromov, which states as follows, that if dimension of your manifold is between 3 and 7, and let's Mn comma G be a complete Riemannian manifold with scalar curvature bigger than equal to 1, then there exists an exhaustion comes 2 with union equal to 1 to infinity, gamma y is m, and gamma i's are n-dimensional compact smooth submanifold with boundary omega I, which admits PS symmetric. And this is the result we'll be using considering n equal to 4 in our situation. And now let me tell you some of the topological tool we need. So one of the tool from topology that we need is a theorem by Friedman. So the topological tool. This is a theorem of Mike Friedman, who says that let W be a contractible compact four manifold with boundary a three sphere, then W is homeomorphic to four ball. And this is sort of one of the results that he even received Fields Medal for. Okay. So these two results and the additional tool that we need is some Floer theoretic invariant that I'll be mentioned when I need it. So plus some Floer theory or gauge theory. So let's use all these to try to sketch a proof for theorem 1. So, oh, sorry, before moving, anybody has any questions or comment regarding any of this statement at this point?
Is that instant on Floer homology?
So, I mean, you can use instanton, but maybe I'll just use Higard Floer. But I think they all are equivalent. So any you can sort of write down the whole argument even in instanton as well.
Okay.
Okay,
Thanks.
great. Yeah. So, sketch of the proof. So so let's say theorem 1. Okay, so it's good to also name them. So yeah, this is our theorem. So here we want to now prove that if you have a compact four manifold whose interior admits a PS symmetric, then it is homeomorphic to four ball. And so because of Friedman's this result, we know now that it is enough if we can prove that the boundary has to be a three sphere. If we can able to prove that this boundary is a three sphere, then at least using Friedman, we can say that this contractible manifold is topologically or homeomorphic to a four ball. Okay, so let's try to argue that why this manifold. So claim that if W is a compact contractible manifold such that interior of W. So the circle over W sometimes call as interior. Let's call this as M, interior of W, which is M, admits uniformly PS symmetric. Then boundary of W is S3. So we'll prove this fact now. So
can I ask one question?
sure, yeah.
So in the theorem that you're going to prove now, you said that okay, W. Okay, so W is the compact.
Yeah. So W. So M is the
I see.
interior. Yeah. So for
W.
let's say W. Yeah.
I see. Okay. Yeah.
Any other question or comment? Okay, great. So let's proceed. And please, again, stop me at any point if something is not clear, because sometimes I could also say something very wrong.
Yeah,
Okay.
I do have another question. Maybe that's then too easy. So if we, of course, W, okay, so we could ask if W admits a positive scalar curvature metric, right? So this property makes sense, but then everything becomes trivial, maybe? Or, I mean, if this is a double compact contractible four manifold,
Mm-hmm.
which admits a positive scalar curvature metric,
Mm-hmm.
which is then automatically uniform,
Mm-hmm.
then we could use your theorem to see that it's the ball, four ball, right? I mean, that's immediate, seems to me. Because then we do have uniformly positive scalar curvature metric in the interior.
Mm-hmm. Is it true though that the interior will have a complete metric?
You say it admits a complete metric of uniform.
Sorry.
I see. Okay. Yeah. Okay. No. It's not clear.
Sorry. Sorry. We need, yes, right. I think I mentioned that in the statement for contractible. Yeah, complete.
Yeah. No, in the statement it's okay.
Sorry.
Maybe we can discuss this then later.
Sure. I'll be happy to, I'll be happy to listen. Okay, sorry. We need all these conditions. If you drop any condition, I don't know what will happen. Thanks. Okay, so since W is a smooth and contractible, so at least we know that the interior of W has a nice exhaustion, which is, you can just think of from the color neighborhood structure, is just boundary W cross 0, infinity, this neighborhood. And so that will give us a nice exhaustion of interior of W by this sort of exhaustion. Okay. Now, besides that, the mu bubble argument gives us another exhaustion, omega sigma I. And again, M is the interior of the W. So this dot is that I'm deleting the boundary. So this is M. So sigma I gives another exhaustions, and we have this that boundary of sigma I is PSC, 3 manifold. Okay, great. So now we can have a compactness argument, since we have now two exhaustion, that by compactness argument, we can argue that one exhaustion contain another exhaustion, in a sense that there exists a J belongs to N and I belongs to N, such that boundary of sigma I completely contain inside boundary W cross 0, J. So pictorially speaking, there will be a slice like this, where this is boundary W cross 0J, and one of the boundary is sort of completely sitting in between this. It could be very wide, but nonetheless, it is completely sitting in a boundary separating way, as this picture. Okay. So now, if we consider the projection map here, so now if we look at the restriction of the projection map, and from omega to boundary W, this is actually a degree 1 map. So this is a degree 1 map. And the property of this degree 1 map saying that, so now we can actually use geometrization. So geometrization then immediately implies that since this is a degree 1 map, that means boundary of W as a 3 manifold admits a PSC metric. Okay.
Can you say a few words how the projection is defined?
So I have the projection map, this, just because this is just standard boundary W cross 0, 1 or boundary W cross 0, J. So you just take the, you just take, this is a
I
four.
see. Okay. Oh, okay. You are in this product, and then you have the projection.
It's a product projection. So the standard, okay. Yeah.
Okay, thank you.
Yeah. And now I'm restricting that projection map as from in this copy, I guess, in this section. And that will give us this map, which is a degree 1 map. Okay. So then geometrization immediately implies that boundary W is a 3 manifold that admits a PSC manifold. Moreover, note that we consider W to be contractible. So that means the homology of boundary W is trivial. Okay, so then again, geometrization comes to the picture, and this gives us a complete list of such possible boundaries. So the boundary could be now either the 3 sphere or the Poincare homology sphere. Let's call it P, or its reverse orientation minus P, or connected sum of any copies. So connected sum of Kp with L minus P. And these are the only possible boundary now we could have on W. Okay, so now I'll introduce Floer theory to discard the possibility of these guys. If I could discard that none of this boundary could be possible, then I'm done, because then S3 could be the unique such possible boundary. Okay, so this is the strategy. So now let's talk a little bit about Floer theory. So I'll not go into any of the complicated details of the Floer theory, but here is sort of the idea how Floer theory could be helpful. So some kind of Floer theory. Okay, so one of the ideas is that if I start with the integer homology 3 sphere Y, then associated to this, I could define a absolutely graded Floer homology, let's say HF. So this is H stand for Higard, F stand for Floer. So Higard Floer homology. And this is defined by Peter Osbath and Zoltan Szabo. Yeah, I truly don't know why they don't call it Osbath-Szabo homology, but they gave the name, so we follow this name. And this is an absolutely graded homology module over this ring Z U inverse. And the group structure or the module structure is as follows. So it has one long tower where the U action sort of going like this, and this tower goes to infinity on the positive direction. And then it has some torsion element, U inverse torsion. These are some kind of U inverse torsion element. And this is an infinite tower. So these groups kind of looks like Z U inverse. Oops, sorry. Direct sum with some kind of torsion element. So this torsion element we usually call as the reduced HF red of Y. Okay. And as I says that this is an absolute graded, and the grading comes from the lower degree of this infinite tower. So this lower degree gives an, we call it in general D of Y. So So you can think of, so usually then we write it as D, which denoting where the lower degree, the Z lying. Okay, and in particular, this is an interesting invariant for three manifold, and that one of the theorem.
Is it finally generated in each degree or something like that, or?
Yeah. So each of these degree is a copy of Z. You can think of these are copies of Z, and the U action is sort of like going like this everywhere. So yeah, so this is finally generated and all nice properties it has. Okay. Any other questions? Okay, great. So what are the properties that this variant works well under nice cobordisms? In particular, so this is theorem by Oswald Szabo, saying that, let's say, if W is a cobordism from Y1 to Y2, that means pictorially you can think of W is a four manifold with two connected boundary Y1 and Y2. And moreover, the homology of W related Yi is trivial, then the minimum grading has to match D of Y1. It has to be equal to D of Y2. Okay. So, and then they also computed various invariant. So this is one property. There are other property of D invariant. One of the interesting properties that connected sum. So D of Y1 connected sum Y2 is nothing but D of Y1 plus D of Y2. And another interesting property is that D of Y is equal to minus D of Y minus Y. So if you reverse the orientation, the grading goes to minus. Okay. And so this immediately tells you that if a three manifold bounds a contractible manifold, four manifold, then the D invariant has to be equal to 0. Because you can take a four ball out and that will give you a cobordism from, oh, sorry, if in case I didn't say that, but let's say this is 0. So after taking a four ball out, we could have a cobordism from S3 to the three manifold, which is now contractible. So there is no homology in between. So then their D invariant has to match. Okay. And moreover, Osbat and Szabo also computed the invariant of the Poincare homology sphere, and they shows that this is equal to 2. And so by this property, D of minus P is minus 2. And we can immediately conclude that D of K, P connected sum L minus P is non-zero if K is not equal to L. So going back to our list now, so we can discard this, and also we can discard any situation where this K is not equal to L. So the only remaining possibility that we could have now is when I have equal number of positive and equal number of, negatively oriented Poincare homology sphere connected sum. Now this is another possibility that could happen to be boundary of a contractible manifold, and at that now we have to deal with. Just to tell you one more thing, that actually this manifold do bounds homology ball. So these manifolds do bound for manifold W such that the homology of W is trivial. Okay. So really, this D invariant at this point is not enough to conclude. However, there is some more tools that gauge theory provides. One of these tools is this famous result of Donaldson's diagonalization theorem, and which is later extended by Taubes. So this is where Donaldson and Taubes come. And what they shows that the basic idea is that Poincare homology sphere cannot bound a negative definite simply connected negative definite simply connected for manifold. Sorry, give me 1 second. I have to phrase it rightly. So, okay, so sorry, Donaldson and Taubes says that connected sum of k Poincare, connected sum of k minus Poincare cannot bound a contractible formula. Sorry, I tried to say something else, but I forgot what I wanted to say initially. But this is a statement using gauge theory, and so if
can you just slide a little bit so we can see the previous part? Sorry. Went under the multicolors. Thank you. That's perfect.
So
I would like to ask a question about exactly that slide. So you say if a three-manifold bounds a contractible four-manifold, then D is equal to 0, and then you proceed in your proof. But do we have that property in the case we are considering? I thought we know that the boundaries admit PSC matrix, and therefore you have your list.
Mm-hmm. And as I said, that in this list, every situation the D invariant is non-zero. So in this situation, D invariant is non-zero. In this situation, D invariant is non-zero, and in this situation also D invariant is non-zero.
Yes.
The only situation where D invariant is 0 is this case.
And why do you know that D is equal to 0, the D invariant in your case?
Because the additive property that D of Y is did I write it correctly? Yeah, D of Y is equal to minus D of minus Y. So so then if you add them together, then this is 2 times K minus L.
Yeah, sure. I mean, that is.
And so if K is not equal to L, this is non-zero. And when K equal to L, this is 0.
And you know that it must be 0?
Yes, it must be 0 because of this result that the D invariant has to, if there is a cobordism which is such that the relative homology is 0, then the D invariant of the lower and upper boundary is same. And so if we take a 4 ball out, then we have a cobordism from S3 to the manifold, and D invariant of S3 is 0.
I see you. You take a 4 ball out.
Yeah.
I somehow missed that point.
Yeah.
Okay, now it's clear. Thank you.
So, okay. So, and then the final possibility where it can be connected sum of Poincare homology sphere and its negative orientation, that is now excluded because of the result of Donaldson's and Taubes. So the only manifold now we are left with is just the S4. So this conclude that boundary W is actually a 3-sphere S3. And so now then Friedman's result implies that W is homeomorphic homeomorphic to B4. Okay. So this concludes first part of the proof. So this conclude, sorry, what is the statement? Yeah, so this conclude this part of the proof. So any questions so far? Okay, so now I will tell you why extra assumption of measure can help us to make it diffeomorphic. So, so now if we on top of that, if we assume this is measure, that means by our hypothesis, W has a handle decomposition with one handle and one two handle. Now we know that from the most theoretic argument that if the descending sphere of the two handle attach the ascending sphere of the one handle exactly at a point, then they can be cancelled out. And in particular, this is the case where it is happening. And to see why is this the case, we need to go back a little bit of more classification result. So our previous result now saying that the boundary has to be a three sphere. And let's try to understand what is the boundary here if we attach a four-dimensional one handle on a four ball. And so B4, the boundary of B4 union one handle is S1 cross S3. So I have a boundary component which is S1 cross S3 here, and I now attach a two-dimensional handle such that, sorry, a four-dimensional two handle, and I get S3 back. So in the theory of surgery, if we look at, we see that we start with S1 cross S3. We consider a knot inside S1 cross S3. And then we did a dense surgery on K and get S3. And this is where a famous result of Davi comes. Davi shows that. So David Davi, in his famous property R conjecture, so this is essentially used to known as property R conjecture. So by David Davi, he shows that in this situation, K has to be an unknot and the dense surgery coefficient has to be 0. So now if we transfer this information to the most theoretic information, this is precisely saying then that the ascending sphere, the ascending sphere of one handle transversally intersect the descending sphere of two handle exactly at one point. And that implies that we can cancel them. And then we're left with just the four ball. And that gives us that then this resultant manifold is diffeomorphic to the four ball. So any question with this part? Okay, great. So this is the idea of, and this completes the theorem one. And again, I'll not go into the details of how theorem 2 could be proved, but here is sort of the idea now, how you could exclude exotic R4s from having such metric. So now let's talk a little bit. By the way, how much time do I left? Can I ask?
Yeah, you can go on. I mean, we had some discussions, 10 minutes.
Okay, great.
Yeah.
So So let me give you some
Can you
idea.
scroll back down for a
Oh,
second,
sorry.
please? You scrolled it up very quickly.
Oh, sorry. Yeah.
Is everyone able to see it?
Wait. Okay. Should I continue?
Of
I
course,
seem to
it's
be having technical problems. Does anyone else have technical problems?
no, I
Okay,
don't.
good. We should continue and don't worry about my problems.
Wait.
Go ahead.
Okay. Sorry.
But maybe you can say again a few words why this, in your situation, you are in the situation that Gabai's result
Mhm.
applies. Maybe I
Yeah.
missed something.
Yeah. So as I said that Gabai's result saying that the attaching sphere
Yeah.
of the two handle has to be along the meridian of the S1 factor of S1
Mhm.
cross. Sorry, this is S1 cross S2, not S3. And that means, and that is precisely the 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 descending sphere of the one handle. So
I see.
they're now
Okay.
transversally intersecting at a point. So that means most theoretic way you can cancel them out.
Okay.
So now this is I'm not going to the details of the exotic R4, but here is sort of the idea of exotic R4. So observation, so let's call it as an observation. So let's try to give you the pictorial observation that if we start with 4 ball and take a disk in the interior, so let's say D be a disk, and the disk is intersecting the boundary as a knot K. So D be a smooth disk in 4 ball, and boundary of D is a knot K. Now we can do that. We can delete a neighborhood of this disk from the 4 manifold, and let's call it this is a new 4 manifold B prime. Pictorially, we just delete a small neighborhood of this. And now, if we attach another 2 handle along the meridian of this knot, so now if we attach a 2 handle where the attaching region meridian of K, then we get back the 4 ball again. Okay, so this is our observation that how surgery theory can give us 4 ball. Okay. Now, instead of attaching an honest 2 handle, we can also replace this 2 handle by a fake 2 handle. A fake 2 handle, or sometimes in literature, this is known as Casson handle. So Andrew Casson constructed such handles, and these are topologically D2 cross D2, which is proven by Mike Friedman, but smoothly may not be D2 cross D2. And if you do so, then if whatever resultant manifold you get may not have a smooth structure, nonetheless, if you consider the interior of such 4 manifolds, it has a smooth structure. So B prime union a Casson handle, and if you take interior of this manifold, this is may not be, so let's say this may not be diffeomorphic to standard R4, because interior of standard 4 ball is standard R4, but this resultant construction may not give you standard R4. And this is in fact proven by many people such as Gomf, Donaldson and all, that this is exotic R4. This is one of the prime construction of exotic R4 that various people such as Taubes, Gomf and many others shows that there are way to construct exotic R4. That is, they are no longer diffeomorphic to the standard R4. Okay, so now we will try to exclude such examples to have uniform PS symmetry. And the idea is similar in a sense that what I have been doing here, but a little bit more structure we need. So one structure we need is some kind of symplectic and contact geometry. Again, I'm not going to the details, but what Gomf essentially showed in his work that this exotic R4 can be given some kind of nice exhaustion. So this is
Anubhav, are all exotic R4s of this kind that one knows of, are they all constructed in this manner?
No, not all, but at least there are like an uncountable class constructed in that manner. There are some other also constructions.
Okay, I see. No, that's just a quick.
Yeah. So I'm just considering this one class that is constructed by Gomf. And the interesting part about Gomf's construction is that Gomf, so if you study carefully, so this is, I think the reference of this is, I think, his annals paper from 1994, where he constructed this. And if you carefully go over this whole construction, you see that his construction gives a very nice exhaustion, where there is an additional structure which is a symplectic or Stein structure. Exhaustions, so plus Stein structure. And now this enable us to actually define a different type of invariant which can understand open manifold. And so as I said before, that between if we have a cobordism, then my Floer maps gives us some kind of interesting maps. And this invariant comes by taking limit of such four maps. So exhaustion plus Stein structure enable us to define limit of Floer maps. And in fact, this is proven to be an well-defined invariant by Gudgill, who calls this as N-Floer homology. So this is in fact an well-defined invariant. Now, so there are two properties we could prove. We could prove that mu bubble implies that N-Floer homology is 0, but existence of Stein cobordism enable us to track contact invariant, which shows that N-Floer homology is non-zero. So that implies that all this construction that Gomf has created cannot have a trivial in-Floer homology. But if we assume that it has a complete uniform PSC metric, then it should have a trivial in-Floer homology. And that's how we could find a contradiction, and we could exclude all these uncountable class from being having existence of such metric. As I said, that these parts require some work and some kind of more concrete structure, but I'm sort of like putting every details under the rug at this point. But this is mostly the idea that we used in the proof. So any question with this? I'm happy to talk if anybody curious about more details. So I would like to end my talk with one question. That's what is the answer? So as I say that, so one of the idea of our proof is sort of destroying the infinity somehow, and then that will obstruct us from having a PSC metric, like uniform complete PSC metric in the four manifold. But how about if we know that the infinity is very nice? Is there a way to then obstruct in such a, for example, here is a question that I really do not know the answer. So question, and I ask few of my friends at this point, what could be an answer? So does punctured K3 has an uniform complete PSC metric? So that is, you take the K3 surface and you take a compact four ball out, and now consider this four manifold. Does it have a uniform PSC metric? I don't know the answer. And another question I could ask is that what happened in all these above theorem if we drop the uniform condition? What happened if we drop the uniform condition? Yeah, these are the two questions I'm really at this point curious about, and I don't know how to understand or answer. But I think this is a good place I stop, and I'm happy to chat and answer any question any of you have. Thanks.